What if 100 prisoners could turn an almost impossible chance of survival into nearly 1 in 3? No cheating, no communication, and no change to the rules. 100 prisoners are brought into a room containing 100 numbered boxes. Inside each box is a slip of paper bearing the number of exactly one prisoner. The slips are shuffled randomly, so every number from 1 to 100 appears once and only once. One at a time, each prisoner enters the room. They may open no more than 50 boxes. Their task is simple: find the slip bearing their own number. After they leave, every box is closed and the room is restored exactly as it was. They cannot leave marks, they cannot move the slips, and they cannot communicate with anyone who enters after them. But here's the terrifying part. If every prisoner finds their number, all 100 of them are released. If even one prisoner fails, they all die. Not a majority, not 99 out of 100. Every single prisoner must succeed. So what should they do? Pick 50 boxes at random? Open boxes 1 through 50? Or simply hope that luck arrives at the most important moment of their lives? For one prisoner, choosing 50 boxes at random gives a 50% chance of success. At first, that does not sound hopeless, but this is not about one prisoner succeeding. It is about 100 prisoners succeeding together. If every prisoner chooses randomly and independently, the probability that all of them survive is 1/2, multiplied by 1/2, 100 times. That is 1/2 raised to the power of 100, approximately 7.89 times 10 to the power of -31. In other words, their chance of survival is roughly 1 in 1.27 nonillion. For all practical purposes, 0. Random guessing is a death sentence, but the prisoners are allowed to meet before the experiment begins. They cannot communicate once it starts, but they can agree on a strategy in advance. And there is one strategy that raises their chance of survival from virtually 0 to more than 31%. Not 31 times higher, not 31,000 times higher. It turns an almost impossible event into something that happens nearly once in every 3 attempts. It sounds like a trick. It feels like the prisoners must be sharing information, but they are not. They are exploiting a hidden structure inside the random arrangement itself. To see that structure, let us shrink the puzzle. Imagine only 4 prisoners and 4 boxes. Each prisoner may open 2 boxes. Suppose box 1 contains the number 3, box 3 contains the number 1, box 2 contains the number 4, and box 4 contains the number 2. Prisoner 1 enters the room. Instead of choosing randomly, they begin with the box carrying their own number, box 1. Inside, they find the number 3. That number determines the next box. They open box 3, and inside it they find their own number, 1. Prisoner 1 succeeds. Their path was 1 to 3 and back to 1. Now prisoner 3 enters. They begin with box 3. Inside it is the number 1, so they open box 1. There they find the number 3. Their path follows the same structure, but from a different starting point, 3 to 1 and back to 3. Prisoner 2 follows box 2 to box 4, where they find the number 2. Prisoner 4 follows box 4 to box 2, where they find the number 4. 4 prisoners appeared to make separate decisions, but the boxes actually contained 2 closed loops. One loop connected 1 and 3, the other connected 2 and 4. In mathematics, each closed loop is called a cycle. Now let us rearrange the slips. Suppose box 1 points to 3, box 3 points to 4, box 4 points to 2, and box 2 points back to 1. Now all 4 numbers belong to a single cycle: 1, 3, 4, 2, and back to 1. This cycle has length 4, but each prisoner may open only 2 boxes. Prisoner 1 opens box 1 and finds 3, then opens box 3 and finds 4. Their 2 attempts are gone before they return to number 1. The same problem affects every prisoner in that cycle. In the 4-prisoner version, cycles of length 1 or 2 are safe. A cycle longer than 2 causes failure. Now return to the original puzzle. The strategy for prisoner number 23 is this. First, open box 23. Read the number inside. Then open the box carrying that number. Read the next number and continue following the chain. Stop only when you find 23, or when you have opened 50 boxes. For example, the path might begin 23 to 71 to 9 to 44 to 62 and eventually back to 23. Every other prisoner follows the same rule, beginning from their own box. Because each number appears exactly once, these paths cannot simply end. No number disappears. No path reaches a dead end. Eventually, every path must return to a number it has already visited. And because the arrangement is a permutation, it returns to its starting point. The random arrangement of 100 slips is therefore not an unstructured mess. It is a collection of separate cycles. There might be a cycle of length 8, another of length 17, another of length 29, and one of length 46. Or there might be one enormous cycle containing 70 prisoners, while the remaining 30 numbers form smaller cycles. Every prisoner follows the cycle containing their own number. If that cycle has 50 or fewer members, they are guaranteed to find their number within 50 attempts. More importantly, every prisoner in that cycle succeeds. But if a cycle contains more than 50 members, its prisoners cannot complete the loop within the allowed number of attempts. Therefore, all 100 prisoners survive if, and only if, the random arrangement contains no cycle longer than 50. The strategy does not give an individual prisoner more than a 50% chance of success. It does something much more powerful. It connects their fates. Instead of producing 100 scattered and independent outcomes, the strategy makes prisoners succeed together or fail together. But one question remains. In a random arrangement of 100 numbers, what is the probability that every cycle has length 50 or less? And how can that probability possibly be greater than 31%? To answer that, we need to count the dangerous cycles. The prisoner puzzle has now become a precise mathematical question. What is the probability that a random permutation of 100 numbers contains a cycle longer than 50? Let us call the length of the largest cycle L. The prisoners succeed when L is less than or equal to 50. They fail when L is greater than 50. So we must calculate the probability of finding a cycle of length 51, 52, 53, all the way to 100. Consider a cycle of some length k, where k is greater than 50. First, we choose which k numbers belong to the cycle. The number of ways to do this is 100, choose k. Next, we arrange those k selected numbers into a cycle. If we were placing them in an ordinary line, there would be k factorial possible arrangements, but a cycle has no unique starting point. For example, the cycle 1 to 3, 3 to 5, and 5 back to 1 is identical to the cycle 3 to 5, 5 to 1, and 1 back to 3. They describe the same loop, viewed from different starting positions. Therefore, the number of distinct cyclic arrangements of k elements is k-1 factorial. Finally, the remaining 100 minus k elements may be arranged in 100 minus k factorial ways. So the number of permutations containing a particular cycle length k is 100, choose k, multiplied by k-1 factorial, multiplied by 100 minus k factorial.
And now the expression collapses beautifully. 100, choose k, equals 100 factorial divided by k factorial times 100 minus k factorial. The 100 minus k factorial terms cancel. K-1 factorial cancels almost all of k factorial, leaving only k. The entire expression becomes 100 factorial divided by k. There are 100 factorial total permutations. So the probability that a random permutation contains a cycle of length k is 100 factorial divided by k, divided again by 100 factorial. Everything cancels except 1 divided by k. The probability of a 51 cycle is 1 divided by 51. The probability of a 52 cycle is 1 divided by 52, and the pattern continues all the way to 1 divided by 100. But can we simply add these probabilities? Usually, adding probabilities directly is dangerous because different events may overlap. A single permutation might satisfy more than one condition, causing us to count it multiple times. Here, however, every dangerous cycle is longer than 50. 2 cycles longer than 50 cannot exist in the same permutation of 100 elements. Even 2 cycles of length 51 would require 102 elements, so each failed arrangement contains at most one dangerous cycle. There is no overlap. Therefore, the exact probability of failure is 1 divided by 51, plus 1 divided by 52, plus 1 divided by 53, and so on, through 1 divided by 100. This sum is approximately 0.688172, so the probability of success is 1 minus that value, and the result is 0.3118278, 31.18%. That is the number hidden inside the puzzle. With random guessing, the group's chance of survival was approximately 1 divided by 2 to the power of 100. With the cycle strategy, the chance becomes nearly 1 in 3. But why does this answer land near 31%? There is a deeper analytical reason. Place the terms 1 divided by 51 through 1 divided by 100 beside one another as thin rectangular columns. Their upper edges closely follow the curve y equals 1 divided by x. The sum of those columns is therefore related to the area beneath that curve, and the integral of 1 divided by x is the natural logarithm of x. The area from 50 to 100 is the natural logarithm of 100 minus the natural logarithm of 50. That simplifies to the natural logarithm of 2, approximately 0.6931. This gives an approximate failure probability near the natural logarithm of 2, so the corresponding success probability approaches 1 minus the natural logarithm of 2, approximately 30.69%. But this is an approximation and a limiting value, not the exact answer for 100 prisoners. For exactly 100 prisoners, the discrete sum gives 31.18%. As the number of prisoners becomes larger and each may open half the boxes, the success probability moves closer and closer to 30.69%. The integral explains the shape of the answer. The finite harmonic sum gives its exact value.
But we do not have to trust the algebra alone. We can test the strategy with a Monte Carlo simulation. In each experiment, we randomly shuffle the numbers from 1 to 100 into the boxes. Then we decompose the resulting permutation into cycles. We measure only one thing, the length of its largest cycle. If the largest cycle has length 50 or less, the experiment is recorded as a success. If it is longer than 50, the experiment is recorded as a failure. Begin with 10 experiments. The result jumps wildly. Perhaps 20% succeed, perhaps 50%. The sample is far too small. Increase the count to 100 experiments. The estimate becomes more stable, but it still fluctuates. Now 1,000, 10,000, 100,000, and finally 1 million random permutations. The experimental success rate settles close to 31.18%. The simulation and the combinatorial proof agree, but a final apparent contradiction remains. Each prisoner opens half the boxes. The chance that any particular prisoner finds their own number is still exactly 50%. So why is the group probability no longer 1 divided by 2 to the power of 100? Because the prisoner's outcomes are no longer independent. That is the real mechanism behind the puzzle. When prisoners choose boxes randomly, one prisoner's success tells us almost nothing about another prisoner's result. Their outcomes behave like 100 separate coin flips. But under the cycle strategy, every prisoner inside the same cycle shares the same fate. If the cycle has length 50 or less, every member succeeds. If the cycle is longer than 50, its members fail. The strategy does not magically increase the probability of individual success. It
It changes the correlation between the prisoners. It reorganizes 100 independent risks into a small collection of shared outcomes. Imagine a random permutation whose cycles have lengths 8, 17, 29, and 46. Every cycle is shorter than 51. Every prisoner succeeds. Now imagine another permutation containing a cycle of length 51. That single cycle is enough to destroy the plan. The whole puzzle is therefore controlled by one hidden global property, the length of the largest cycle. Nothing about the arrangement stopped being random. The prisoners received no additional information. They did not mark the boxes. They did not communicate. They simply agreed to navigate the randomness in a consistent way. And that reveals the deeper lesson. Random does not mean structureless. A shuffled deck has structure. A random network has structure. A permutation has cycles. And once that hidden structure is recognized, a problem that looked like 100 independent guesses becomes a single question about the largest loop. With random selection, the prisoners are almost certain to die. With the cycle strategy, they all walk free in nearly 1 out of every 3 possible arrangements. Not because they defeated probability, not because they got lucky, but because they understood what probability had built. Start with your own number. Follow the chain, and let the cycle lead you home. This is the hidden mechanism inside the 100 prisoners puzzle. Sometimes, the difference between an impossible outcome and a real chance of survival is a pattern that was there all along.